In this video, we'll be overviewing the concept of displacement, or the change in position of an object over a time interval. Through this process, we're going to see why sometimes just describing an object based on its position is sometimes not as useful when we could be talking about displacement instead. So to start off, I've got us a buggy here. It's moving at a constant rate over 4 seconds. We can see that because it goes the same position, change in position over each time interval. And we're going to start just by making a position versus time graph for this buggy. I've defined my origin to be at the start of my number line here, and the positive direction to be to the right. The highlight here I want to make is that this choice of origin was completely arbitrary. The observer, in this case me, decided to make this spot the 0 point. A different observer, a different physicist looking at this, could have chosen somewhere else to be my 0 point, and that's going to be very important as we go forward here. So I'm going to start just by plotting this buggy on a position versus time graph. I see at 0 seconds it's at 1 meter, and then it seems every 2 seconds it goes up a meter. So at 2 seconds it's at 2, 1 second be halfway, and then at 4 seconds it's at 3 meters. And it's going at a constant rate. Now if I had drawn this perfectly to scale, this line would go through all the points, but we're pretty close there. I'm just going to make sure it actually starts in the right spot. So this would be my position versus time graph for this buggy. I could also create a velocity versus time graph. And to do that, I would have to figure out what the slope of my position versus time graph is. The slope of this line will give me the velocity of the buggy at any time here because the slope stays the same. It's the same steepness. So find slope, I'm going to look at rise over run. So I'm just going to do the 2 furthest points. It goes up 2 meters over the 4 seconds. So I have a rise of +2 over 4 seconds. That's 2 over 4. So my velocity is going to be 2 meters over 4 seconds, 0.5 meters per second. I'm going to note I got this 2 meters by doing, I ended at 3 meters minus my starting position of 1 meter. So that was doing my final minus my initial positions at those 2 different times, 0 seconds and 4 seconds. So now I can say, well, this is the same everywhere because it was a straight line. So 0.5 meters per second. And it's going to be right here, positive, going in the positive direction on my velocity versus time graph, 0.5 meters per second. Now, let's say a different observer looked at the motion of this buggy, and they decided they were going to put the origin over here, right in the middle. So they're going to say this is their 0 meters, and they can do that. You know, where you put the origin is arbitrary. And they're still saying to the right is positive, so this would be 1 meter. And have -1 meter. Now it's true that in some cases different origins make things easier, but they could have chosen this to be their coordinate axis. In this case, my position versus time graph is going to look a little bit different. At 0 seconds, the buggy is at -2 meters. At 2 seconds, it's at -1 meter. At 4 seconds, it's at the origin. And I'll connect those with a line again. I'm not drawing perfectly to scale, but you get the idea here. Now we'll see these 2 position graphs look different. It's the same motion, but it's just being described a little bit differently based on the observer's choice of where they put the 0 point. They could have also chosen a different positive direction, but we won't do that here. Again, I could find the velocity of this object. It's moving at a constant rate, so I can do rise over run in this case. In this case, my rise, which is going to be my final minus my initial, I ended at 0 minus -2 meters. So that's going to be +2. So And this should agree with what I got before because it's still the same motion. So the buggy is still going 2 meters to the right. In either case, that would be able to see its displacement. And again, the time interval is 4 seconds. So once more, I get a velocity of 2 meters over 4 seconds, 0.5 meters per second. And again, it's a positive velocity. Even though I was in the negative positions here, my velocity, my slope, was still the same, positive 0.5 meters per second. So let's add that to our graph here. Oops, I want to get this to draw my line straight. There we go, 0.5 meters per second. And so what we'll see here is even though I have two different position graphs for the same motion, I end up with identical velocity versus time graphs. So this is why in some cases the position graph is not as useful because this chosen origin was arbitrary. So we can end up with a different looking graph, whereas in both cases we end up with the same velocity. Because even if we choose a different starting point, different origin, which will affect our intercept, we still have the same motion. This buggy is still moving at the same rate. So we end up with the same slope and therefore the same velocity versus time graph. And we'll notice when we did that, we had the same time interval and we also had the same displacement. It's the same motion. So in either case, the buggy changed its position from 0 seconds to 4 seconds. It changed its position by positive 2 meters. So this is a more useful quantity because it didn't depend. It didn't depend on where we said 0 is. So I could say the buggy's at 1 meter, a position of 1 meter, the buggy's at a position of 3 meters. Well, this guy says the buggy's at a position of negative 2 meters, and then the buggy's at a position of 0 meters. And we'd both be correct. We just have chosen different spots. We would both agree, however, that this buggy has a displacement, a change in its position of 2 meters. So that's what displacement is. Displacement is going to be the change in position of an object over a time interval. This is how we're going to write it. We're going to use the Greek symbol delta. Delta just means change in. So displacement is the change in x standing here for the x position, which is the final minus the initial position, because that is how we found that velocity, right? Rise over run. Well, the rise is the delta x. It's the change in position. One thing I want to note here is how displacement is different from distance traveled. If I'm over here and I'm starting on the 5 meter mark and I walk over to the negative 1 meter and then back to the 3 meter. Well, over the course of that motion, let's put where I was initially again. I've gone, I go 6 meters this way and then I go back this way another 4. That would be a total distance traveled. I've gone 6 and then 4. That's a total distance traveled of 10 meters. My displacement, however, is negative 2 meters. I've walked 10 meters, but my change in position, where I ended versus where I started, is only a change of negative 2. I've gone 2 meters in the negative direction over the course of whatever time interval it took me to do this motion. All right, so that's the difference between displacement versus distance traveled. Sometimes they're the same thing. If I just walked in one direction, it might have ended up they were the same thing. But in this case where I've gone multiple ways, my displacement ends up being very different from my distance traveled. All right, so now we're going to look at how do I find displacement from our various models. With the motion diagram, it's pretty straightforward. I just measure where I am versus where I started. Position versus time graph is also similar. So if I wanted to find the displacement here from 1 to 5 seconds, I'd say, okay, where am I at 1 second? Well, looks like I am at, I believe that ends up being 4.5. Maybe I should have picked some better numbers here. You can take my word or you can do the math. That's negative 4.5 meters at 1 second. And at 5 seconds, here I am, regretting my choice of slope here. This is 1.5 meters. So my delta x, I can just look at how it's changed between these two times. So final minus initial, 1.5 meters minus negative 4.5 meters. So here we can see it's again important to pay attention to direction. This is a negative. Subtracting a negative gives me a positive. So I go up 6 meters from 1 to 5 seconds. If you did the slope calculations, you would find that the velocity in this case, I go up 6 meters. I did that from 1 to 5, so that's a run of 4 seconds, going from 1 second to 5 seconds. So don't make the mistake of saying 0 to 5 here. 6 meters over 4 seconds is 1.5 meters per second. So here I have below it the velocity graph for this motion, or 1.5 meters per second is the slope of my position over time graph. And here's the real nice thing about the velocity versus time graph. It does not tell me where the object is. I can't look at this graph and know where this object started or where it ended up. What I can use this graph to do, however, is find the displacement. So if I want to know, again, that displacement from 1 to 5 seconds, there's a little geometry here I can do. So we're starting at 1 second to 5 seconds. And I know how fast it's going. So if I were to say to you, I'm traveling in my car at 25 miles per hour, how far do I go in 4 hours? Well, you'd say, okay, 25 miles per hour times 4 hours, that's 100 miles. And you'd be right. We can do something similar here. I'm traveling from 1 to 5 seconds, so that's, you can see we're kind of working backwards from what we did above. That's 4 seconds as my time interval. Put that right over here. And how fast am I going? I'm going at 1.5 meters per second. So I could say, okay, 1.5 meters per second times 4 seconds. Well, you've got a displacement of 6 meters, which is what we found above on the position graph. But let's look at how that's represented graphically, because this will be really important when we get to the next part of this unit. What I'm doing here is I'm doing one number multiplied by another. I'm doing this number multiplied by this number. And if you sort of squint a little bit, you can see that that's making a rectangle. I've got a base of 4 seconds and a height of 1.5 seconds. So this is how we can graphically represent displacement on a velocity versus time graph as an area. This is called the area under the curve. And that is going to be the change in position. So when I do 1.5 times 4, I'm doing the area of a rectangle, base times height. So that's a really, really critical idea going forward in this unit, is that displacement, the change in position of an object, can be found by the area under the line on the velocity versus time graph. Note, if I was going in the opposite direction, if I was going like, I don't know, negative 1 meter per second, and I wanted to find, again, from maybe, let's say from 0 to 3 seconds, I would look for this area. So in 3 seconds, going at -1, I'd go -3 meters. So that's how I would do it in the case where I'm traveling in the negative direction. Okay. All right, a little practice if you want it. Finding displacement using this idea of area under the curve. pause the video here and check these out. I'm now going to go into them, so then you can unpause and follow along with me. We're going to find the displacement for these different scenarios. All right. So in this case, first I always want to think about what is the object doing. Let's see. It's moving in the positive direction at 1 meter per second. It's going to stop for 2 seconds, and then it's going to continue in the positive direction for another 2 seconds, traveling at twice its original speed. So it's going to be going at 2 meters per second here. And I want to find, let's see, the displacement from 2 to 3 seconds. So I'm going to look for the area. This is a little bit of a trick right off the bat. 2 to 3 seconds, there's no area here. The line is right on the axis of the graph, and that's what we're doing. We're finding the area to the axis, basically. So here, my displacement is 0 meters. During that time interval, it doesn't go anywhere. It has no velocity. All right, 0 to 6 seconds. Well, this is sort of broken up into parts, right? I got this and this and this thing here, so let's look at each one individually. First 2 seconds, I'm going at 1 meter per second. For 2 seconds, that's going to be 2 meters. That's this 1 meter times this 2 seconds. And then we said here I don't go anywhere for those next 2 seconds. And then here I go 2 meters per second. This is meters per second over here. For 2 seconds. Well, that gives me an area of 4 meters. That should make sense. You know, here I'm going twice as fast as here for the same amount of time, so I go twice the change in position. So overall, I went 2 meters, I stopped, I went 4 meters. My overall displacement would be those two areas put together, 6 meters. Okay, here we got a little bit of a trickier one. Now, what time is the object at its starting position? So if it's back at its starting position, that means that its final position equals its initial position. And in that case, if we're thinking in terms of displacement, change in position is 0. So when is my displacement 0? When do I get 0 area under my curve? Well, obviously at time equals 0, it's at its starting spot, but where else? Let's start doing some areas. I want to figure out when can I get the total area to be 0. And I should have mentioned this earlier. If I have a negative velocity, I'm going to get a negative area. So let's start there. Here I'm going at, looks like negative 1.5 meters per second, and I'm doing that for 2 seconds. So that would give me a displacement here of negative 3 meters. Okay. If I did this whole thing here, 1 meter per second, 6 seconds, that would be an area of 6 meters. Well, those aren't going to add up to 0, so I know I can't have traveled this whole time. So I'm wondering, what time are these two areas going to cancel each other out? So when am I going to get 3 meters up here? Well, I have a height of 1 meter per second. So what do I need time-wise to get this area to add up to be 3 meters? Well, 3 times 1 is 3, so it's going to be 3 seconds. So if I start at 2, it's going to be to the 5-second mark. So I find that at what time is the object at its starting position? And it's going to be at the 5-second mark. So after exactly 5 seconds, this object will be back where it started. It's going in the negative direction, then it turns around and goes in the positive direction. Determine the object's position at 6 seconds. This is a little tricky, so I'm gonna do it maybe the way a student would, and they'd say, okay, 6 seconds, that's here. So I'm going to find the area all the way across, and I would find 6 times 1 is 6, or sorry, not 6. This is a change of 4 seconds. So 4 times 1 meter per second is 4 meters. So maybe 4 meters plus negative 3 meters. That's the displacement over the whole interval, so from 0 to 6 seconds. That's a displacement of 1 meter. So I go 3 in the negative, then 4 in the positive. Now, that's not what we're being asked for, though. We're being asked, what is its position at 6 seconds? All of this velocity graph is able to tell me, though, is the change in position. So I don't know. I don't know where this object is. Sure, if it started at the origin, it would be at 1 meter. But this graph does not tell me where the object started. It just told me how it was moving. The object could have started at, I don't know, the 10 meter mark, 10 meters in the positive direction, in which case its position would now be 11 meters. All I know from the velocity graph is the displacement. And this is why we'll often use displacement, because we don't really care about the original position. That's completely up to whoever came up with their coordinate axis, whoever determined where the origin is. As we saw before, the displacement will always be the same. So we don't have to worry about where did we put the origin. So that's why we like to talk in terms of displacement. So that's displacement, and that's how to find it using the area under the curve of the velocity graph. Again, when I say under, if it's negative, you're actually going up, but that's just how we say it. All right.